Welcome to the discussion on measurement bias. Brief introduction was the metrology handbook is out. Heather Wade Group, you can get a signed copy for the exact same price from ASQ, shipped to your door from Heather Wade. The other discussion points here is on our website. Be sure to always check our website. If you're not following us, please consider following us. We have the new paper draft of Let's Talk About Bias, Measurement Bias, which I'm going to put in the chat window as well. Those are watching later online can just go to our website and so I had a lot of fun writing the paper, and there's also a blog, and the blog will have links to everything. But a lot of fun writing this paper when I started off, and you always think, well, what happens if we don't correct this? What happens if we just assume an accuracy spec and we have known errors and we're just saying, it's covered in the accuracy spec? What happens when we make another subsequent measurement and then another measurement after that and another one after that? And the general assumption here, and we can kind of poll people as they come in, is that people probably are not correcting for bias. They want some adjustments, probably short-term adjustments. They want to set as close to nominal as possible, and then they want to go use their instrumentation, or they want a tech to go use their instrumentation. And really what we're supposed to do, and I'm going to cover it, is when we look at ISO 17025, or we just look at good practice, we want to talk to people about when do you want this adjusted? And if somebody says, I want it adjusted if it's out of spec, or I always want it adjusted, or I'll correct for it. These are things we want to have the discussion with our customers on and know the exact expectation of the equipment and how they're using it. So with that said, I'm just going to talk a little bit here. Importance about force. People have seen this before, I'm sure. Though I like showing these pictures of collapsed bridges, highway spans, pre-stress, post-tension, another bridge collapse there, a hotel collapse in Miami. And it's really what drives us. Our purpose is to create a safer world and help people with their force and torque measurements. We do not cover all things metrology. We're specifically force and torque. But then we branch out into these other topics like the bias, which covers almost all aspects of metrology, right? If my instrument has a bias, what do I do? So what we're going to talk about here is what's it happen with force? I mean, you can apply this to almost any discipline, but specifically the examples here are the force discipline. To start, let's put everything together, right? And this is our measurement confidence. It's taken from good to great. It's a kind of a rebrand of the businesses. What are you passionate about? What can be the best of the world at, and what drives your economic engine? So it works really well with metrology. If we put three circles together and we say, hey, if we know our measurement uncertainty, we know our metrological traceability, and we're in agreement on the freaking decision rules that we're going to use, we can establish this measurement confidence. And once we establish it, we're going to have to do some other things to make sure we're with where we want to be. And we'll cover that throughout this session as well. But there's some things here in the standard. 6.51, laboratory shall establish and maintain metrological traceability of its measurement results by means of documented unbroken chain of calibrations, each contributing to the measurement uncertainty, linking them to an appropriate reference. Now, this is important because if we do not, the reason it's important, because if we do not correct for bias, we're really possibly not going to grab our uncertainties correctly. We'll talk a little bit more about that. But for those new or been through it before, measurement uncertainty data is cumulative from one level to the hierarchy from the other. So if we start at SI, everything's traceable to SI, not NIST. A lot of people like to say traceable to NIST because that's what their customers are expecting when you get to different tiers and everything else. I want to make sure I'm NIST traceable. Now, it's really traceable to the SI through an NMI. And there's more to it than that. But what this is basically saying is if I send equipment for calibration to somebody, I have to absorb their measurement uncertainty as well as mine. And it's just going to keep growing and growing and growing and growing and growing. So if I can send my equipment to NIST, I'm probably going to get a measurement with the lowest uncertainty. Now, if my equipment's not good, meaning reproducibility and repeatability and some of those other things aren't nearly what they should be, then my uncertainty is going to suffer. So you have a lot of things to consider in there. You have the reference standard, and I'll start showing that in a little bit. But Here's a typical tier for force. NIST redid their weights after 50 some years, and they're making measurements up to 1 million pounds, 4.4 meganewtons, to about 4 to 5 parts per million. And then we send our weights to NIST to be calibrated. We send our secondary instruments to NIST to be calibrated. And on the weights, we're about double NIST. We're absorbing their uncertainties from when they calibrate their weights, and we're doing repeatability studies, and we're doing all kinds of things, SPC and everything else. And our uncertainties are higher than this. And then the next level down, people that send to us, their uncertainties are going to be higher, and so on. Hopefully everybody gets that. But when we start looking at calculating uncertainty correctly, which is important in this bias discussion, because if we don't grab that bias, we're missing a potential large portion of our uncertainty. But CMC is defined as calibration and measurement capability, and it often includes things such as resolution, repeatability, reproducibility, reference standard uncertainty, reference standard stability. This is one of my peeves here on reference standard stability, because it's the change from one calibration to the next. And when I talk about this, I should do a full webinar on it, is if your accuracy specification of your device is something like 0.1% of full scale, and you send it in for calibration and the lab reports that it was out by 0.2%, there's a problem there if on your scope you're saying I can make measurements within 0.1%. And I see people do this all the time, is they use accuracy in lieu of uncertainty, and they don't get all the contributors. So people are here, started the education process. This is the easy 5 R's and the E, but there's a lot of stuff on measurement uncertainty. But ISO IEC 17025 says laboratories shall identify the contributions to measurement uncertainty, blah, 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 and then it goes one evaluating. Measurement uncertainty, all contributions that are significant, including those arising from sampling, shall be taken into account using appropriate methods of analysis. So all contributions that are of significance. So if we have an error that we know about and we don't correct it, what do we do? Again, back into bias. So if we examine some things for primary standards on a load cell, you can start looking at the end result on this. We calibrated a secondary load cell 1 point. We got reproducibility. That one set to 0 because of this ASTM lower limit factor. More on that later, but that's that U-7643 LLF is actually the reproducibility in this situation, because the calibration is done in accordance with ASTM E74. But we have repeatability, we have resolution, environmental, all the things here. Our CMC, that's a reference standard, 14.43% of the overall budget. And on this particular item, it's their end result is 10,000 pound load cell at the 10,000 pound point, they's 0.004%. Just simple math. If I scaled this down to 10% of capacity, I'd probably be looking at 0.04%. Another mistake some labs tend to make is they do 1 point and then say, I'm good making measurements to that. But this is at capacity. So the difference between dead weight and load cells, obviously load cells are really, really good at capacity, but when you use them at 10%, 5% of their loading range, the uncertainties go way up as a percentage of implied. If we look at this on that uncertainty tier, if accredited lab, instead of using dead weights, the expanded uncertainty is almost 10 times that. It's at 0.04%, and that accredited cal supplier calibrating the same load cell would be at 95.74% of the contribution, just from that reference standard uncertainty that all labs have to absorb. Now, just graphing it out, you can see the difference on our graph. You can see all the different pieces, and when it's dominant, you just see the one chart there, and there's about the 10 times different. So why is measurement uncertainty important? Okay, now we're getting into more sections. If we remember that the measurement confidence chart, we have measurement uncertainty, we have measurement traceability, and now we have a decision rule. And 761 says, shall document the decision rule employed, taking into account the level of risk such as false accept and false reject and statistical assumptions. Hey, I signed up for this webinar on bias. Why are we talking about this? It all comes together. That's why we're talking about it. So we need to report the risk, and if we're not correcting for bias, the reason this is in here is because later on, hopefully I do a good job and put it all together, And you could say, hey, if I'm not accounting for that and I'm making a decision pass fail, that risk level is going to be a lot higher than what I think it may be. So decision rule is a rule that describes how measurement uncertainty is accounted for when stating conformity with a specified requirement. All this is pointing back to bias with this measurement uncertainty, measurement uncertainty, measurement uncertainty. And if I want to make this statement of confirmation, this comes from ILAC G8, which I love this picture. I have two scenarios here. An A, scenario A over here, real easy to look at, right? If I'm taking everything into account, if I can find my A on here, right? Everything's within my band. I have a lower limit, nominal, upper limit, everything's within. And then B, something's wrong here. Could it be repeatability? Could it be some bias? Could it be reproducibility? My type A's, my type B's, whatever it is, it looks like a third is hanging over. And we can make, with our calibrated eyeballs, we could probably say, yeah, that looks, maybe it's a quarter, the way that graph is drawn. Maybe this is 25% risk. We'll show this graphically in a little bit. Here's a situation that you're going to find three scenarios in that Metrology Handbook 3rd edition on decision rules. A situation that some people would call this good when it's actually the risk is quite high. And remember, the standard said we're going to report, right, the level of risk. So I have a nominal value, 10,000, whatever, newtons, force units, whatever, and my measured value is 10,010. So with that being said, I report 10,000, 10,010. The upper specification limit is right on that 10,010. And if you notice right here, look, half of our curve is outside of the 10,010. This is where you see some of those posts on LinkedIn and everything else. No, thank you. Labs that allow simple acceptance, no, thank you. I don't want 50% of the risk. All of these. And then those that are pretty astute will say, well, your TUR on this is almost 1-to-1. Well, if I had a 4-to-1 TUR, it could be a lot better, right? That would limit my risk because a lot of people request just 4-to-1 TUR. So, okay, we change it to 4-to-1. Notice anything change here? Change the TUR to 4-to-1. I'm still at the measured value. This measured value is still right at the specification limit. If I can use the mouse and draw well, which I cannot. So still right at the specification limit. And the percentage that is hanging over that specification limit right there is 50% of this, right? 50% of my graphs. That means when you receive this instrument, there's a 50% chance of it being good or a 50% chance of it being bad. And our TUR or TAR, all this, our CPK is 0, which is an interesting concept. If you want more on that, you can go to our YouTube videos. But that takes into account the location of the measurement. Very, very, very good tool. So hopefully we started to talk about a little bit about decision rules. Haven't named them all, measurement uncertainty. And then we go to this TUR and what is TUR? And those that do not know, it's the ratio of span of the tolerance to the quantity to subject to twice the 95% expanded uncertainty. This definition right here comes out of ANSI Z540.3 handbook, and it talks about what shall be the minimum contributors, and also ILAC P14 section 5354 around there also discusses about the short-term contributors that go in there. So from deduction basically on it, you have the CMC, which is your reference, the resolution of the device, and repeatability. Big shout out here to Jeff Gust, if those that know him. He does a segment, I've been doing it on Facebook and LinkedIn called Metrology Mondays, where he was talking about P14 pretty recently. I suggest following him if you do not. His segments are very good. But that's it. We're talking about TUR. We're talking about the tolerance. What is that? Divided by my calibration process uncertainty, which is defined in that denominator right there. So hopefully people are getting a sense basically of what's going on. And there are important assumptions associated with using a TUR as a metric. And some people say this 4-to-1 or better. There's other standards, which I'm calling it out right now. ASME B89.1 states that when accessing conformity with a simple acceptance decision rule with a TUR of 4 or greater than 4 shall be used. And I'm saying, look, it doesn't account for the location of the measurement. That can pass you as an unsuspecting or now suspecting, now that you've attended this webinar, up to 50% of the risk. Is if you want it, that's fine. If you agree to it, this standard basically says you can pass 50% of the risk. Now, chances are you're not going to pass it because there's also some stuff about your process and some other things, but it's there. It can happen. So more on guard banding. Here's instrument, and now instead of loading, the upper specification limit's 10,010. Measured value on this one is 10,009, which is going to start leading into our bias discussion. So my measured value is 10,000, and someone sends the instrument to us, and we report 10,009. And we say, look, our TUR is 58.7, CPK 5.9, TAR 62.5. Everything is looking good. We set our allowable PFA to 2.5 or 5% total risk. And if we look at our risk, everything is good. We can even say we make repeat measurements, and it's constantly, whenever we load it to 10,000 pounds, it's 10,009. So you get there. This is chapter 30 of the metrology handbook. When we look at this little type 1, type 2 error, some people may be familiar with this. It's consumer's risk. It's an error probability of false accept, the PFA, and then producer's risk is on the other side, type 1 error probability of false reject. Here's the risk debate, right, in all of this criteria. If I'm a calibration laboratory and I need to take measurement uncertainty into account, and I start failing more instruments because of this, that my costs could go up. I'm giving less bad instrumentation, less risk to my customer, but operating a laboratory could be problematic. And that's when you get into a lot of decision rules, and we have information on that a little later. But just in general, setting the stage for this. And then consumer's risk is, hey, something bad gets out there, right? Something bad enters the marketplace, and that could create problems. And there's a lot more of this discussion in that chapter 30 of the metrology handbook. But this is what people are pretty much accustomed to see. And when you have your accuracy and precision, you have a device with, high precision, small random area. I think everybody on this call wants all their devices to be here. And then there's probably some people that say this is our next best scenario, or others say this is the next best scenario. Personally, our scatter, our repeatability data in here is quite large. This is that instrument that if you send it to NIST, they do multiple measurements, then certainly it's probably not going to be that much better than if you send it to us or a secondary cal lab, because you have pretty much a wide dispersion of the data. And I think we all can agree that this one right here is probably problematic. But why I like this second one, this number 2 here, if we all agree that this is the second best, I mean, some people will say bottom left, is it has high bias. And what happens here, like this becomes almost known systematic error where, hey, guess what? If I just adjust it, or if I apply a correction, I can get that right back on center. And that's what we're going to talk about. And there it is. So nominal value of 10, measured value of 10, we can say there's no bias, no error. Some people like to call it measurement error. Some people like to call it systematic error. When I had the pleasure of writing this paper, I did a lot of research into the VIM and everything else, and there's a lot of different terms because we all need to speak the same language, and there's a lot of different terms under here, and there's no one right way or wrong way. I think the best is known systematic error is probably the best discussion on this, but I think a lot of people understand the term bias. So second graph here, nominal value of 10, measured value of 11.75. Easy math here, right? Everybody, that's 11.75 minus 10 is what? So I have 1.75 bias. If I make another measurement and it's 11.75, now I have repeated measurements with this bias. Now I'm getting to a situation where it's easily correctable. If I get a third measurement where I have this, and then I have a fourth measurement where I have this, now I can correct this. right? I have a little bit of variation there, but I can overall I could apply a 1.75 correction and I have very little error after that remaining. So our example here is we loaded an instrument, right, to 10,000 pounds of, well, applied 10,000 pounds of force to the instrument, and it read 10,009. Total risk, 0. We pass this to the customer. Customer can, there's zero chance, I mean, there's zero risk on here. However, let's go a little bit further. There's a bias of 9 pounds in this example. Apply 2, someone's going to say, what about replicate measurement? So we do it twice. It's a good thing. The resolution's pretty coarse, which is why that needs to be included in the denominator. But we do coarse resolution, and we make multiple measurements. Each time we load it to 10,000 pounds, it reads 10,009. Okay? So now I think it is safe to say that we have a known systematic error. And someone say, well, what is that? Well, this is where you go to the Vim and you start looking at it, and you look at this other reference here that I'm going to highly recommend. Systematic error is an error that, when fully quantified, is predictable. Systematic error can be a bias, an offset in the measurement, or an error based on independent parameters such as known temperature dependency. If the systematic error is known, a correction should be applied to the measurement result. Again, since the true value can never be known, use of the term systematic error is discouraged unless referring to qualitative known can be corrected. That gets a little confusing on here, but this is in section 2.2, Introduction to Statistics and Metrology. I highly recommend this book. It's from a lot of people down at Sandia. They just did a great job. And what they're basically saying when we correct for a known bias, we have typical people are used to seeing this type B evaluation, which is your difference from nominal or your bias in this result, right? You've seen this graph numerous times. And then the type A is repeatability. I'm just going to write repeatability with my mouse because I'm not the greatest writer with that. I really need a stylus. But so if we're looking at really values, true values never really known, right? We know it within, in our measurement case, we know it within plus or minus 0.0016 or 16 parts per million. And then we know that the instrument could have some repeatability. The example I showed, the instrument, this curve was really, really narrow as the repeatability. And I'll show that in the next graph here. Look, really narrow. This thing repeats, right? All my uncertainties accounted for, and my distribution is next to nothing. So, and this slide shows the comparison between two different suppliers, resulting in different TUR values. The bottom graph shows the higher risk level using a different supplier. The new provider has higher measurement uncertainty of about 0.025% than shown in figure 1. And this is the top scenario, low risk scenario, where the calibration provider had, and this one 0016. Everything else has remained the same. However, the overall measurement risk on supplier 2 is circled as 21.19%. The assumption that the measurement bias is known, plus 9 newtons in this example, although the risk is 21.19, the bias can usually be corrected, adjusting the measuring system or incorporating in a measurement model as a correction. Using the high risk scenario, we will discuss what happens when bias is not corrected. So it's high risk again. This is exactly the same thing shown again. Measure multiple measurements. We know that the bias is that. The problem we have is what happens when we do not correct for this bias. The customer got this number. They were told their system is in spec, and to generate 10,000 newtons of force, they have to load their instrument till it reads 10,009. Now, if they just load their instrument till it reads 10,000, what do you think is going to happen? They're going to be off by 9 pounds, right, in the other direction. Likely, when they load their instrument to 10,000, it's just going to be 999. This is what they're actually going to apply to the customer's device, the customer that they are calibrating the instrument for. We've already done the cal and say, hey, at 10,000, this device should read 10,009. They can correct it. So The reference standard is not loaded to 10,009. Instead, they load the device to 10,000, which means only 9,991 is applied. That's at 10,000 minus that 9 bias. There could be additional corrections, linearity, and all that. So we're making some assumptions on this, but in general, it's going to be, we can all agree that's likely going to be close to 9. We show not correcting for this 9-pound bias graphically by subtracting 9 newtons from the result, from the measured value. The UUT, their UUT, because they're not loading it properly, now reads 9987 newtons, which could result in a lab failing the instrument and deciding to adjust the device within the acceptance limits. So if we look at this, they're 9 pounds off. The customer's acceptance limit for this device could be plus or minus 10 pounds. If they loaded their device till it read 10,009 to apply 10,000, that would have shifted the customer's device to read 9996. So this 9 pounds is really going to cost that customer of theirs to fail this. The lab's likely going to fail the instrument and adjust it where it would not need to be adjusted. And if we apply this on the risk graph of not adjusting that known systematic error or bias, the total risk becomes 87.67%. So very, very significant. And this happens all the time. You say, hey, this is my accuracy specification. Lab told me it was in. I'm just going to keep chugging along. And am I going to account for it in my uncertainty? I don't know. I have a feeling that a lot of labs do not account for it in their uncertainty. So this is a sad situation where if they correct for it, the device, the customer that they are calibrating the instrument for, their device is in. Now it's 87.67 and they adjust it. So of course, the right thing to do is what happens when we correct for bias. The right thing for the end user to do is load the device to 10,009 to apply 10,000. Let's assume they do that and they do this and they calibrate another instrument. And if they do, in this case, their uncertainty is larger, TUR, almost 2 to 1. But it's about that section in the standard about accounting for risk, 1.02%. So the reference standard being loaded to 10,009 to apply 10,000, their uncertainty of their measurement here is plus or minus 5.178. That's with the repeatability, with the resolution, absorbing everything they need to absorb. And they're going to call it in. The risk is less than 2%. Hopefully they had a contract review with their customer. And, right, instead of a fail, it's a pass. And if this is your equipment, I'm sure you would rather know the right value instead of constantly shifting this bias down the chain. So now we get into following this logic further with JCGM 106, and they talk about calibration process uncertainty and conformity is defined as the probability that a non-conforming item will be accepted based on a future measurement result. So there we have our measurement traceability. This is what we're going to use for the next few examples in this scenario, right? Primary cal, 01, 0.17, 2.5, 3.3, 5, and 10. And I'll show you why. But if we follow this logic progression through the calibration primary level through the pyramid, correcting for bias and not correcting for at each step, in that case, we can generate random variations due to the measurement uncertainty at each level. When we do not correct for bias, measurement uncertainty might be underestimated and therefore may not align with the definition of metrological traceability, undermining measurement confidence. That is a lot to think about. Hey, I'm not correcting my bias. I have this error. I'm just going to let it fly. And are my measurements technically metrologically traceable? I'm kind of leaning no. When I started this, I was really questioning it going through the standards. And right now, I'm kind of leaning no. It's an interesting discussion. If people are in the text chat, whatever, they can say, yes, they are, they aren't, this is why. But it was certainly an interesting discussion for sure. And Paul Reese, I think in 2018, he submitted an NCSLI on these corrections, correcting for short-term and long-term. Is there a definitive answer? And I think he he left at a different topic, but it was more on the do I correct the standard, or do I just, apply correction? And I think it was indeterminate, the end result on that. But you can go search. He has a lot of his stuff published, and I can, of course, send that link if anybody's interested. But so what happens when we do not correct measurement uncertainties? Here's the tier. I did this purposely. The second level, if somebody started with us, right, the second is the 10 pound plus or minus 10 pounds. They're your TR 4 to 1, 3 to 1, 2 to 1, 1 to 1. And here's just randomly generated values. Measured value with bias versus measured value bias removed, which is corrected. Look at this. If we follow all our measurements down, right? This first one, 9991, right? They didn't load, they loaded to 10,000 instead of 10,009, so they're 9 pounds off. If we follow this logic downward, you can just see randomly generating within the uncertainty how many, just from the second level, 4 to 1 TR down, right here would probably trigger adjustment points. So this lab would adjust, then the next one, then the next one, then the next one. There are chances that it could go in and out, and I'll show you that in these graphs. But look, if we correct it, every single time when we correct the bias and remove the bias, this is within the specification limit, even when we had a 1-to-1 TR. Now that can go out. That's just the sample we ran. And here's some of the lines here with these different samples. So not correcting for bias, and then bias corrected. So the blue line is the bias corrected. The orange line is not correcting for bias. So if it starts at the reference, remember JCGM, if it starts at the reference and then people do not correct for it, it's just going to affect all the measurements downward from when that bias is not corrected. In this scenario, many instruments may have failed when they would have passed calibration. And then I just have another simulation here, different. You can see it run random. And I'm actually going to go to this tab because Dilip and I created it. It's a fun worksheet here. Everybody, I got to move my GoToMeeting. But I created the cell. It's a pretty complicated sheet, but not too bad. Tier 1, we assume this tier has been corrected in these results, and then it generates bias. So we can set these to whatever we want. We can say the measured value is 10,009. We can say it's 9991. We can do 9991, right? And if I just look at this graph here, and just randomly generate. So what are the probabilities? And these are all within the uncertainties. You can see it go either way, right? In this scenario, the uncertainties are so large that the process TUR 1-to-1 actually comes in, just depending. So there's some probability theories here, of course, in the uncertainties and just randomly generating numbers to put in different graphs. But more times than not, if you just start watching the simulations, even that last one, 9982, we're looking for plus or minus 10. 9997, there, that's in. 10,007, there, it's in. We're just looking for different simulations, there, it's out. But when you correct for the bias, that blue line, every single time, your risk is just so much lower than the other one. The other one, you could have things going, what's the song? Go your own way. You could have things go your own way. Chances are they're not going to go that way. And with this graph, we can run back to our simulation. Plus or minus 10 pounds. Bias is 9 there. We'll go back to 10,009. I changed it up just to show different scenario. We go back to this scenario. You can see bias corrected. Every level is plus or minus 10 pounds. Bias not corrected. There, it only fails at the last cal point. Just running random number generator with uncertainties. So sometimes it's in, sometimes it's out. Like I said, look at the yellow line there. It's way out. So just interesting observations here and a cool little simulation for the purpose of this webinar. But there it's out. If we look at these points graphically on that first one that I ran, I didn't make this would have taken forever to make this more dynamic. But if we just look at it from the first level on, that lab with the 4 to 1 TUR does not correct for bias and randomly generate the numbers, right? And if we do so, you can start seeing the risk here. 78.81%, 3 to 1 TUR, the bias, see that bias -9. Then that lab performs a cal for somebody else. Their bias is now -13. They don't adjust for it. The next lab, risk lessened because it's random. Now the bias is -11, and by the end, the bias was -20 with this. But in all of these situations, the risk was pretty high on that one scenario. And if we correct for bias, by the time we get down to a 1 to 1 TUR, gets risky and hairy anyway, but by the time we get down for bias is next to nothing, but the total risk is 4.76. But 1 to 1 TURs are very difficult. You hardly have any room on your measurement to be within to make a pass compliance decision if you're holding your PFA, probability of false accept, or risk to less than 2%. So you can see it. If I correct it, if I remove that systematic error from the equation, I'm good. And then here's what I was kind of alluding to. TUR will determine, it's really going to set the percent of specification. So if I have plus or minus 10 pounds and I have a 58.79 TUR, and I want to take measurement uncertainty into account, 98.33% of the specification. So this is what this is saying. I'm saying table for 95% confidence, 5% total risk. And this table is giving me the upper and lower guard band risk. So Morehouse is, if we receive an instrument, as long as that instrument reads between this, we can take measurement uncertainty into account, and we can make a pass decision in accordance with ILAC G8 method of the 2.5 PFA, 5% total risk. Now, if I had a 4 to 1 TUR, that shrinks my acceptance limits, 3 to 1 shrinks it, and then when we get down to that 1 to 1, I really do not have much much wiggle room at all to be within the specification. So the assumption here, like most books, most papers that you read, the assumption here is that the measurements are centered. It's something that us as a metrology community need to get out of, in the fact that we need to get out of just assuming everything's centered all the time. It's really, TUR formulas work. Work for us, however, if the end user has not considered and corrected for the contribution of the effective bias in their evaluation of measurement uncertainty, the acceptance criteria may be skewed. Skewed acceptance criteria can increase measurement risk at all tiers, starting from the first tier of the pyramid that did not correct for bias correctly. Back to that conformity assessment, right? And when an instrument is good, it might have been adjusted to the wrong number if the bias was not corrected. If we continue to generate data randomly, we might end up with the table and graphs below. This should matter to you because when there is bias that is ignored, meaning not corrected or not included in the lab's calibration and measurement capability and uncertainty parameter, measurement traceability is not achieved, and all subsequent measurements are not traceable. That's the stance I'm taking on this. Like I said, I'm up for debate very much, but here, just reference, people are saying, oh, then every time I have my instruments, you're saying I should adjust them because I don't want my technician to shift them. Well, there's multiple ways to correct for bias. This meter down at the bottom right is one of our several force indicators that use coefficients. So basically, when we do the calibration, we don't even use it in force units. We go into the A to D counts, generate a set of coefficients, and we know that set of coefficients is going to predict and get that number or that load cell's behavior as close as possible, or not eliminate the bias, but all but remove the bias from the equation. So instead of being 9 pounds out at 10,000, you might be 0.2 or 0.3 or 0.4 pounds out at 10,000, which that's a lot easier pill to swallow if we go back to our, I can go back to it here. So what happens if, let's just say we're 1 pound out. And let's say I can calculate things right. If I'm 1 pound out, what do these numbers look like? Wow, I need to regenerate that graph because it's here, if I'm 1 pound out, look at the line bias not corrected. It's all those measurements are still plus or minus, yeah, still plus or minus 10 pounds, right? If we're just looking at randomly generating numbers. So you still have some additional error that you might want to correct, but it's not nearly as bad if you can get it as close to nominal as possible. Resolution, I stuck this in here because I always like sticking in things about resolution, and some people will say you don't need resolution for TUR, and this graph is just basically saying you do, because when the resolution is considered, the TUR starts at 6.25 to 1, and then you can see that graph TUR with resolution. So the coarser the resolution, the lower the TUR gets. That's all we're showing here, and I like P14 and ANSI Z540.3 handbook both confirm that in that denominator resolution needs to be there. And this is why, because we could essentially set our resolution very coarse. And if we set our resolution very coarse, we could get our repeatability down to 0. And if we got our repeatability down to 0, guess what? Now we can't detect hardly anything. Decision rules. Oh boy, they're fun, right? Anybody's in there, a lot of labs didn't have measurement uncertainty figured out, and then they go and they add all these decision rules, and these are just a sampling of the decision rules. We talked about these examples. We had some method 5 in here, and we had ILAC, which is in, oh, there's the G8 method, which is in there. They're simple. TOR, UCAS, RSS is not RDS, RP10, Fluke R, yeah, M6. There's still M2, M1. There's just a lot, and you're supposed to have a conversation with your customer about decision rules and what, and it's probably why a lot of labs have gone to the shared risk approach, and kind of people don't understand it, and then there's a possibility that they're going to pass you all the risk, and I wouldn't take it. If I was a lab, I just wouldn't take it. That's my stance on that. I would insist on a decision rule that makes sense. I mean, you can also argue you could run in probabilities, you can run all this other stuff, but at the end of the day, we want, in general, we want the confidence that the lab calibrating our instruments accounted for known biases, and that we have our 3 pillars of measurement covered. And once we do this, we correct for bias, then we just need to prove our capability, which here's a little bit of advertisements for us because we're offering force PT kits. Is section 7.72. The laboratory shall monitor its performance by comparison with results of other laboratories where available and appropriate. This monitoring shall be planned and reviewed. That shall include, but not limited to, either or both of the following: participation and proficiency testing. And this one is, participation and proficiency testing. We have load cell kits. Once you have everything accounted for, you can go in and, I like to say, close the circle, close the loop, do whatever. Say, I've calculated everything out. I think I'm making measurements this good. I do a qualified PT in which I can prove out that yes, I have. Now, if I don't pass my PT, maybe I've not accounted for something. Maybe I haven't reduced that bias, that 9-pound bias, that as soon as I reduce it, I would absolutely pass my PT. Don't know. After we prove out our capability, we need to plan to monitor our results. That's section 7.73. Data from monitoring activities shall be analyzed, used for control, and if applicable, improve the laboratory's activities. If the results of analysis of data from monitoring are found to be outside predefined criteria, appropriate action shall be taken to prevent incorrect results from being reported. So we're kind of a lot better at this than we were. I'm still not happy. Our frequency, here's just some SPC checks that we're doing. And I'm getting I'm getting happier with these results because what we're doing is comparing results between different machines, different time frames. And I'm using a few methods. I'm not going to go into them in detail, but I'm using Z-score and EN ratio in addition to control limits, which I'll show you that data as well. And I really like these. I think Z-score's an interesting one because it really is dependent on this standard deviation. So if you have one machine that's giving you really tight standard deviation and another one that's not, there's something that's going on, and it can detect it quite well. And then the EN ratio is just comparing I have this device and the uncertainties in both. But what we normally look at is like Schuart's control charts here, which you can see the different machines, and as long as we're within the upper and lower bounds. But the thing is with load cells, and the reason I stuck this in here with the bias discussion is with load cells, sometimes you have drifts or shifts that occur. So this graph is by itself doesn't give the whole picture. But when we start looking at the EN ratios and the z-scores, they give us a much better picture than just that graph, because if you were only testing um, a new load cell, once or twice a year, there is a chance that they could go out, different technicians and everything else. And that's where you need to do further diagnostics, and that z-score and the EN really comes in well. So if my upper bound went out and my EN and my z-score were good, I'd rely less on my SPC data and wait for the next time I took data to see if it's going to stay out, and which would be a shift in my unit under test or my artifact, as opposed to a shift in my equipment, especially if the test is robust and you're closing it by doing PT tests. So conclusion, using the manufacturer's accuracy specification and not correcting for bias can further increase measurement risk. We did sampling by varying the TUR that everybody saw, generated values randomly by correcting for bias and then by not correcting for bias, which showed a significant difference in the measurement risk. And not correcting for bias seems to be a problem many in the calibration deal with, and their unsuspecting customers are likely getting calibrations that carry too much overall risk. The risk of not correcting for this offset bias should concern anyone making measurements. And then in addition, here's some of my jabs. The habit of insisting on a 4-to-1 TUR only works if the measurement process is centered, which is measurement biases are corrected. And then JCGM 106 references that when a measuring system is used in conformity assessment, that the measuring system has been corrected for all recognized significant errors, biases. And then when bias is not corrected, the risk of making measurements that does not properly account for bias can result in an underestimation of measurement uncertainty and therefore disagrees with the metrological traceability definition and undermines measurement confidence. So yes, if we're looking at that metrological traceability definition, right, an unbroken chain of comparisons, right, each contributing to the measurement uncertainty. And if our measurement uncertainty is not accounted for properly, do we have measurement traceability? Morehouse has many options with our force calibration system that use coefficients generated at the time of calibration. 4215 plus, this is my favorite, polynomial cal, ASDME 74, ASU 376. Just go in, do everything in millivolts. It'll correct to force units. And what we report, the ASTM lower limit factor, is the lion's share of the uncertainty, which is the reproducibility condition, which is all captured in that interpolation error is captured in that standard. So they get programmed in. Other common issues, CMC values, not realistic, lack of understanding, guidance documents, probability of false accept. If you ask us to make a compliance decision, we'll report it all the time. We report the PFAs, and then replicating instruments. Those that have attended my other webinars know I'm very passionate about adapters and replicating how things are being used when they're calibrating, and not making spelling error there. I need a proofreader. Not making the proper corrections, bias, and correcting for weights for force. If people saw earlier, they can go to our download page. I had that up here. We have under documentation and tools, the let's talk about bias paper if you want to share that. But there's also like spreadsheet tools, software, and other things. There's a CMC uncertainty made easy. I don't know if it's made easy, but it absolutely gives you the directions on how to use it. But there's also force to mass conversion tools, and there's bias in general in these. If I download it here live, if I don't correct, this is a known error, right? If I know that I have my gravity is different than the lab that did the cow, and I'm using mass weights instead of force weights, and I don't correct for the at least the gravity and the air density and stuff, guess what? Look, gravity and buoyancy biases right there. This is a difference. This is mass to force. It also has force to mass. You can look at this total error difference. But yeah, this is these some of these are biases, right? You different gravity and different, and we know what those errors are, so we can correct for them. So bias goes far beyond just, hey, it read this and read that. It's also in correcting if anybody's using force or if anybody's using mass weights to generate forces, you need to be correcting them for your local gravity and your air density and material density to remove those additional biases. So it stems a lot further than what's just discussed today. So coming up April 12th, if you're looking at calibration software, we have free software to download. And Zach, our programmer, has been taking this software and doing all kinds of nifty things where you can just take a digital cert and drop in coefficients instead of having to type them. Um, these coefficients, again, they help eliminate measurement bias, and they're easily imported from our certificates, which also means no more typos. I call them fat finger typos because anybody knows you type a character, what, 7, 8 digits off of a cert, and you do 4 or 5 of those. You can make typos pretty easily. Allows for 7 more digits to be displayed. He added Peak Valley and a bunch more. So that'll be Zach, April 12th. He'll be going over everything with everyone that wants to just see our software. Again, it's free to download. It works with a bunch of meters, some that aren't even our meters, just in hopes to reduce bias from these equations. Because what typically happens is people just want to load it till their instrument reads the number, not to what we say it needs to read. If we say it needs to read 10,009, they just want to load their device to 10,000. So more information, YouTube videos, like I said, a measurement conference, free downloads, the LinkedIn page, anything else, please follow us. Please subscribe to our channels. Anything. I certainly appreciate everyone's time. I hope there were some good takeaways. I hope people download that paper on bias. I really had an enjoyable time writing it, and thank you for listening to me for an hour. Spew all measurement uncertainty and bias related topics. So I cannot thank you enough. At this point, I will take any questions if anybody has them. I turned off the recording, so anybody that wants to view this later, we will have it posted. But if anybody has any questions in the chat, I'm more than happy to. They don't have to only be about bias, but if you have any questions that are lingering that you want answered, there's 30 people. Some dropped in, some left, but like I said, and you can have a copy of this presentation. I'll go fix my spelling errors that I noted, and even though I tried yesterday to catch them all, I went through it. I still caught 2 as I was presenting, which was funny. Not funny for me, but but it happens. So, but yeah, thank you everybody. I'll wait around like a minute or two and see if any questions come in. But yeah, thank you Heather for joining and sharing that link again. The metrology handbook. Heather has signed copies. She ships them out rather quickly, and can't say enough for that experience on working with the ASQ. There is an Ohio regional coming in October that we will be presenting at. So anybody that's in ASQ that's wants to know more about that, just look at your calendar. It's October in Ohio. And MSC is coming up in April. We'll be at MSC, and NCSLI is in Orlando this year. If people are on the fence about going, the Rosen Hotel is quite excellent, and I would highly, highly recommend it. And I'll be there, and I can answer questions in person. Yay! But yeah, thanks everybody. Thanks for your time. I didn't see any questions come in. Hopefully people have grasped this material, and I have my own notes. It's my first time through, and I have my own notes to make it better. If you have any feedback for me and want to email me, please do. Please put it in the chat, whatever. Can't thank you guys enough, guys, gals enough for your time.